Welcome to This Explainer. Today, we're going to do something really cool. Instead of just staring at static, abstract architecture diagrams, we are going to track a single data request through the entire Kubernetes ecosystem. Think of it like a high-stakes relay race. You type a command, hit enter, and boom, a baton is passed flawlessly through this massive gauntlet of complex systems until your application is finally running. So let's jump right in and see how Kubernetes actually pulls off this magic.
Here's the roadmap for our journey today. First, the request journey begins. Second, etcd, the cluster vault. Third, the scheduling cycle. Fourth, custom scheduler plugins. And finally, pod binding and execution.
Okay, Section 1. The request journey begins. The inciting incident of our story is a user, maybe you, submitting a desired state request. You type kubectl apply and that request shoots straight over to the Kube API server. This component is the central entry point for all operations, right? It's the literal front door to your entire cluster.
But, the API server doesn't just leave that door wide open for anyone. Before your request is actually accepted, it has to run this exact pipeline gauntlet through the API server's internals. First up, authentication. Essentially, are you who you say you are? Second is authorization, usually relying on RBAC, asking, do you actually have the permissions to pull this off? Third, the admission controllers step in, and these are powerful. They can modify or just flat out reject your request based on cluster policies. And finally, validation. This just makes sure your request is structurally sound. It's only after surviving this entire pipeline that your request finally gets the green light.
Moving right along to Section 2, etcd, the cluster vault. Once your request is validated, the desired state needs to be immortalized. It has to be written down so the cluster doesn't forget it. And that brings us to etcd. This is the absolute highly secure vault for your cluster's desired state. It's a distributed key value store, and it's strongly consistent because it runs on the Raft consensus algorithm. Think of Raft consensus like a really strict, uncompromising jury. The majority absolutely must agree before any record is officially written down. Every single piece of configuration, your deployments, your nodes, your secrets, it all lives right here.
And honestly, this brilliantly illustrates why high availability is totally non-negotiable here. Because etcd stores all those critical objects, secrets, config maps, and CRDs. Running in production means you absolutely need an odd-numbered node deployment, like 3, 5, or 7 members. Why odd numbers? To maintain quorum. Because if you lose etcd, you literally lose your entire cluster state. If this vault burns down, the cluster basically gets amnesia. And that is exactly why supporting snapshots, backups, and disaster recovery at this specific layer is absolutely crucial. It's your ultimate safety net.
Okay, Section 3, the scheduling cycle. Let's talk about finding a node.
So now that our request is safely tucked away in etcd, the controller manager sees those API changes and reconciles the state. Suddenly, we've got a pod that needs to run, but it doesn't have a node assigned yet. This is where the Kube scheduler steps in as the ultimate matchmaker. It takes the pod through this really rigid micronarrative, a strict sequence of evaluation phases. It starts in the queue. Then the filter phase ruthlessly eliminates nodes that simply cannot run the pod. Maybe they don't have enough CPU or memory. The nodes that actually survive that enter the score phase, getting ranked based on things like affinity, tolerations, and topological spread constraints. Once a winner emerges from the pack, the scheduler will reserve the resources, permit the placement, and finally execute the bind.
Which brings us to Section 4. Custom scheduler plugins and advanced placement logic.
Now, scheduling isn't always one-size-fits-all. Standard CPU and memory filtering is perfectly fine for basic web apps, but for complex workloads, we need rule benders. Looking at this, there's a really clear difference between the two main types of plugin evaluations. Think of the filter plugin as a strict bouncer at a club. It evaluates hard requirements. If a node has a certain taint and your pod lacks the right toleration, or if the node affinity just doesn't match, boom, the node is out. The score plugin, on the other hand, is more like a judge. It evaluates soft preferences, assigning points to the surviving nodes based on resource availability or topology spread constraints, really just to make sure your app is highly available across the infrastructure.
And man, here is where it gets incredibly powerful. For highly complex placements, we're talking GPU workloads or AI and ML clusters, you can utilize custom extension points like pre-filter or post-filter to write your very own custom placement logic. Got latency-sensitive apps? You can leverage entirely distinct scheduling profiles. And the absolute coolest part?
For cost-aware scheduling, you don't even have to spin up a completely separate scheduler. You can just run multiple custom scheduling profiles inside a single scheduler instance. Your pods simply select the right one by throwing a scheduler name into their config. It is super elegant.
Finally, Section 5, Pod Binding and Execution. Time to actually run this workload.
We have officially reached the climax of our journey here. The control plane has evaluated everything. The scheduler has run its gauntlet of filters and scores, the match has been made, and it's time for the node itself to take over. The scheduler successfully binds the pod to a node by writing that decision back to the API server and ultimately into Etsy. This is a huge pivot point because it officially ends the control plane's primary matchmaking role for this specific request. The baton is officially handed off.
And that baton is passed straight to the kubelet. Think of the kubelet as the node's site manager. It's the dedicated agent running right there on the node itself. It communicates directly with the API server, basically constantly asking, hey, do you have any new pods assigned to my node? When it sees our newly bound pod, it rolls up its sleeves and takes over. It manages the actual life cycle, spins things up, and executes those crucial health probes to make sure the app actually stays healthy over time.
But, the kubelet doesn't do all the heavy lifting alone. Working right alongside it on the node, we have two other critical components, Kube-Proxy and the CRI. Kube-Proxy is what implements your Kubernetes services. It handles all that complex network routing using rules like IP tables, IPVS, or even eBPF, making sure traffic can actually reach your pod. Meanwhile, the CRI, the Container Runtime Interface, is the standard interface that takes the kubelet's instructions and talks to common runtimes, like Containerd or CRIO. It physically pulls the image and spins up the actual containers to fulfill that very first request we made.
What an incredible relay race, right? We've tracked this whole resilient journey from that initial kubectl command, through the API server gauntlet, into the etcd vault, through the scheduler's complex matchmaking, all the way down to the kubelet and CRI doing their thing on the node. But as we wrap up this explainer, I want to leave you with a really common architectural interview question to ponder. If etcd is the absolute vault holding this entire process together, what really happens to your architecture if it fails and you lose your quorum? Think back to what we said about high availability and Raft consensus. I highly encourage you to dive deeper into that one. Thanks so much for joining me on this journey, and keep learning.